will see is how to do denoising. Denoising and deblurring at the same time. So let's say that you have an image like this one. Okay, so it is an image. They have taken a picture, but the camera has moved, and we already know how to model that. So our image formation model in that case, simply that the camera moves, is that the image observed is an ideal image composed with a kernel. And then this kernel will have something like some shape like this. That is the handshaking that has been applied when we took the picture. Okay, so this is the result. The problem is that we don't know what the kernel is, and also we will expand this and add noise. So we will add some noise signal. So the idea is, can I have an estimate? This hat here is estimate rather than fully transfer. That is our typical thing. So can we have an estimate of what is the idea based on the observation and maybe some properties of the noise? And the typical properties that we will need is the power spectrum of the noise. So given the power spectrum of the noise and the observed image, can we estimate what the ideal image is? And also in this program where we don't have the kernel, I will also try to estimate the kernel. The problem that we will see in our lecture will not have this kernel. Okay, so we will assume that the kernel is now. So let's see how they do it. Let's see that the results rather than how they do it. Okay, so this is the original image, the one that has been acquired, and this is the deblurred one. So we will be able to go from here, estimate what is the deblur, what is the ideal image, and also what is the kernel. So it has been convolved with that thing. So when you took the picture, you first moved following this pattern. So that is what we will try to do. Okay, so let's do it. Okay, so this is this lecture here today, and we will distinguish correlated noise from uncorrelated noise. So uncorrelated noise, both have the same model. So both refer to this kind of model. But the difference is what is the nature of N. So the nature of N, what is the power spectrum of N? So if it is uncorrelated noise, so you may be familiar with these expressions. Noise, that is noise that follows the IID distribution with Gaussian. So what? There are many letters there. Do you remember what IID is? What is it? Independent and identical distributed. Okay, so there are a couple of letters there. So there are independent, and the other one is identical. So what does it mean? Let's do it in 1D, okay, because it is simpler to represent. Okay, so let's say that we have samples. We have a noise. My noise will be noise of N. N is the sample. And then we have something that is completely noisy. Okay? So it is some noise there. So independent means that given any two samples, so the definition of independence, the noise at the sample and the noise at another sample, so at another location. So you are familiar with this notion of realizations, right? You know the realization of an stochastic processes. Stochastic process. Do you know what that is? So you observe this process. Process is a signal. So you observe this process, you get this shape. You observe it again, and you get a completely different shape. So it is random, but it has some common properties. Okay, so for instance, the mean could be the same, the autocorrelation could be the same, the standard deviation could be the same. So the statistical properties are the same, but the specific values are different. Okay, so we have a realization. So this is our signal. This is the joint. This is the joint distribution. This is the joint distribution of the two, and if it's independent, it is the product of the two. So that is the definition of independence. So that is independence. That for us was the red. Independence. And that means that given a sample, we don't know anything about the other samples. That is independent. Okay, good. And independent, so if it is correlated, it implies that it is dependent. And the other way around. If it is dependent, it is correlated. If it is uncorrelated, it does not mean that it is independent. The other way around is that. So in this direction it works. So if something is independent, it is uncorrelated. And the reason is, what is correlation then? What is correlation? So you may remember from statistics, correlation between, I will call this N1 and N2. Okay, so those are two random variables. So the correlation between a couple of variables, random variables, it is the expected value of N1 minus the mean of N1 times N2 minus the mean of N2 divided by the expected value, the square root of this N1 minus the mean of N1 squared, and the expected value of N2 minus mu2 squared. This is the definition of correlation. So that means that if these holds, if things are independent, then the correlation is zero. The correlation between these two values, two random variables, is zero. In this direction, it works. In the other direction, it doesn't work. So in the other direction, for instance, you can have distributions. So for instance, let's say that we have a couple of random variables, n1 and n2, and they're distributed like this. Okay, so you have values around the city. Okay, this is the where the samples are. Aren't those two variables independent? They are not. So given n1, n2 is either here or here, and it has a few values that it can take, but it cannot take any value. So you may compare this one to this typical Gaussian 2D distribution, n1 and n2, where we have kind of values everywhere. So given one of the n1s, n2 can take all these values. So it is independent. Okay. So a 2D Gaussian, not always, but depends on what the correlation matrix is, but can be independent, and typically these rounded shapes, they are independent. Okay, so independence means uncorrelation. Correlation means dependence, but uncorrelation doesn't mean independence. Okay? Okay, good. So this was one of the letters. What about the other letter? There were a couple of letters there. One was independent, the other one was identical. So identical refers to what is the distribution? What is the distribution of a single of those variables? So this is the distribution of noise n1. And identical means that this doesn't depend on n1. All the variables are identically distributed. So if you say independent and identical distributed following a Gaussian, then this is a Gaussian. This is a Gaussian. Typically with zero mean and some standard deviation, some variance. So when you define noise, you have to define what is the distribution of one of the samples, while the other one, independent, means what happens with pairs of variables. Okay, so one refers to just one sample, the other one refers to pairs. I have drawn two consecutive pairs, or consecutive samples. It could be this one and this one. Okay, so what happens with pairs of samples? Okay, so if something is, how do I know? How do I know if there is a correlation? There is a correlation between these two variables. What will be a suitable characterization of that dependence? What function do you know that can tell you what happens with pairs of variables? The correlation function. So the correlation, right? Again. So the correlation between of a signal and a pair of samples, n1 and n2, is what is the expected value of n1 minus the mean of n1, n2 minus the mean of n2. So, if this correlation only depends on the difference between the two samples, and 2 minus and 1 is the distance between those two. This is called the lag. Typically this will represent with the letter N. So then the process is said to be, the noise is said to be stationary. Have you heard that before? Stationary noise? So stationary means that it does not depend. So the relationship between a pair of variables or a pair of samples depends on how far they are from each other. They don't depend on where they happen. So our signal that goes somewhere here. So these two variables are equally related as these other two. So the relationship between these two is the same as the relationship between these two, because the separation between these two is 1, the separation between these two is also 1. So the relationship here is also the relationship there. If that doesn't happen, so the relationship here is different from this relationship because this happens earlier, then the signal is not stationary. So stationarity means the autocorrelation does not depend on time. So it is not that at the beginning you have some autocorrelation and then you have a different autocorrelation. The autocorrelation is fixed all the time. So now we go back to our slide. So we have two kinds of noises, uncorrelated noise and correlated noise. So uncorrelated noise means given a sample, given the noise at a given sample, you don't know anything else about the noise in any other sample. So for instance, typically the noise in cameras is CCD arrays are the technology for the cameras. So the noise in cameras, so if you have some noise in one of the pixels, you don't know what will happen in any other pixel. Or in film photography, silver light grains. So it is made, this film photography is made of crystals of silver light. And then what happens in one of the crystals doesn't have anything to do with what happens in any other crystal. Our neurons are also noisy. So the noise in one of our neurons in the retina doesn't have anything to do with the noise in any other neuron and so on. Okay, correlated noise. So correlated noise means that given a sample, you know a bit what's happening somewhere else. So look at this image where we have infrasets. So given the interference, or given the noise that you have at the point, you know what is happening in very far points because this noise is very much correlated. So when you have interferences, electromagnetic interferences, or you have these half-tone moire patterns because of the printing, then the noise is correlated. So in this lecture today, we will focus on this kind of noise. In the next one, we will focus on this kind of noise. Okay, so the difference between the two is just the autocorrelation function. Okay, so let's model our image formation. So we will say that the observed image is the ideal one plus noise, and this is in real space, and you can do the Fourier transform of this equation, and you have the same equation, but now in the Fourier space.
But why we don't have the convolution with the kernel that you have?
Yeah, so for the moment we don't have the kernel, and later we will add the kernel. So here, what is implicit kernel? So if you want to put a kernel, what kernel do you have to put here?
Convolution with H.
With a?
H.
With a delta. So if you convolve an image with a delta, you get the same image. So the kernel is a delta, it's just a single point. But we will add the kernel later. And here are some representations of these ideas I've been talking. So let's say that here we have uncorrelated noise. So the noise is, here it is also independent. So every point has a different, has a value that is independent of all the other values in the image. So, and that value can be Gaussian distributed, it can be uniformly distributed, or it can be salt and pepper. So for instance, Gaussian is the one that we are most familiar with, and it looks like this, a Gaussian image, a Gaussian noise image. Uniformly noise images, they look like this. So you see that the pattern is different. And it can take any value between 0 and 255 with the same probability. In the Gaussian, values around the mean are more likely than values away from the mean. And the salt and pepper is, you have a kind of zero value, and this zero value, sometimes you have a 255, sometimes. So let's say that the image is 128, so that is the mean, and then sometimes you have 255, and some other times you have 0. So you have this kind of distribution with normal values, the gray ones, and then from time to time you have a white point, and from time to time you have a black point. And that happens in cameras. So in cameras, let's say that one of the pixels is, for some reason, is dead. So it doesn't read anything. It will give you a black point all the time. And it could be dead on the other side. So let's say that it is short circuit. So it reads maximum value all the time. So you have a white point there. And these are fixed patterns, but this salt and pepper noise, it happens also in some applications. Okay, so, and you can have also Gaussian noise in color images. So each one of the bands has a Gaussian distribution. You can have a uniform in color band. And yeah, this is just an example of the Gaussian image, Gaussian noise image. So this histogram, it is not normalized. I mean, you normalize by the number of pixels. So you divide this by the number of pixels. This would tell you what is the probability that if I take a value at random in this image, I have a value 150, and that would be the probability.
Y-axis, we have the total number of pixels.
In here?
Yes.
No, this is the maximum count. So it has been found that, I don't know, 130 has been found 3,000 times. The total number of pixels is larger. It is the sum of all these values. Okay, so yeah, the autocorrelation function, we have already autocorrelation, we have not defined. So we have defined correlation, but not autocorrelation. Okay, so let's define the autocorrelation. So let's say that we have an image, and we want to calculate what is the autocorrelation of that image with a lag. And this lag is a 2D vector. Okay, so it is like 1, 2, or so it is a displacement. In general, it belongs to set squared. Okay, so it is any two integers. So this is the expected value of the image at n minus the mean of the image times the n is a vector also, because it is a relation, and then that image at n plus n minus the mean range. So that is, and this is simply the average of all the image values. So that is the definition of the autocorrelation. And just a reminder, this you already know, the Fourier transform. So the Fourier transform of the autocorrelation is what? The power spectrum density. So it is the power spectrum density of that image. This is the power spectrum density. This appeared when we introduced the Fourier transform. Okay, so this is the autocorrelation function. So here it is the same expression, but I think mine is more clear. So this is just a way to compute the expectation, and then you have the centered images, and the centered images is the standard image minus the mean, and then you have to include the shift, and then this function here is what happens. So what I'm doing here is you have an image. Okay, so let's make this image. Let's use colors. Okay, so let's make this image red. Let's make this image blue. So you have the red image. So you have the red image, and this one is a shift one. So let's make it simple. Just shift to the right. So, and now I'm computing the product between the two. So I'm computing what is the product of this red value with the blue one, but there is no blue one there. So let's go to the region where they overlap. So for all these points, I'm computing the product of the blue and the red, and then I'm computing the average of that. That is that expectation. Okay, so what happens here in these areas? So here there is no overlapping. Here there is no overlapping. So what I can do is something called wrapping. So wrapping, this is different from yesterday. Yesterday we saw warping. Warping is different. Okay? So wrapping is whatever comes from the left. So this part from the left, I put it back here on this side, and then I can compute this product too. Okay? How do I do that? So one possibility is to use this modulus functions. Okay, so let's. This has appeared probably when you study discrete signals. Okay, so let's look at it. Okay, so let's say that I have a signal. Let me make it simple. So we have a signal that is just one half, 1/3. Okay, and all the others are 0. So let's say this is x of n, and this is n. And I construct the following. So I construct x tilde n, that is, for instance, let's make it like this, x of n plus 1 and modulo 3, because I have only 3 samples here. Okay, so I will construct that thing. Okay, so what does it look like? Okay, so this will be now x tilde n. Okay, so x tilde 0 is x at 1. Okay, so this will be 1/2. X tilde 1 will be x of 2. So that will be 1/3. And then x tilde 2 is x of 3, but 3 modulo 3. So it is the remainder of 3 divided by 3. That is 0. So that goes back to 1. And if you keep on doing, you will see that this is repeated all the time. And on this side, it is the same. So on this side, -1 modulo 3 is also 0. So, so this is 1/3, this is 1/2, so on. So it is a periodization. Actually, making this module, bringing this module is simply periodizing. So this is the way of, you see, for instance, I have shifted this signal. Let me highlight this block. So if you shift this to the left, the sample that goes out comes from the right. Okay, so using the module, it's just a way of whatever comes from one side, I put it back on the other side. And I can use that trick to take this side on this side. So that is what has been done here. So I think now we understand better this autocorrelation equation here. So we have the autocorrelation, and then the autocorrelation is the two shifted images. So shifted down in gray, shifted by the mean of the image, and then we have periodized, and we have displaced our image. Okay, good. Then just to see a bit the properties of this noise. So we have independent noise. So if noise is independent, the autocorrelation should be just delta. And the power spectrum of the Fourier transform of the delta is a constant. But it is not constant because it is realization of noise, but it is almost constant. Actually, the difference between a realization and so you see here that is using the sums. So the sum is for a specific realization, and I have been using expectations. So expectations is if you make many realizations and you compute the average of those infinitely many realizations, then you get what you expect. So for instance, the autocorrelation, what you expect is a delta. For a particular realization, you don't get exactly delta. Delta should be 0 everywhere. Here you have a little bit of noise. But if you take many realizations of this kind of noisy images, and you compute the average of the autocorrelation, you get a delta. And the same for the power spectrum. So the power spectrum of independent noise should be flat. And it is not exactly flat. There is a little bit of noise. But if you take many realizations of these and you compute the average of all those realizations, you get it flat.
But we can see that the autocorrelation is the inverse Fourier transform of the power spectrum, and in the whiteboard you write that it was the power spectrum without the inverse.
Yeah. So let's put it here. So it is two. So we have autocorrelation, and we have I dropped the arguments. So if you want to go in one direction, you have to do Fourier transform. If you want to go in this direction, you have to do inverse Fourier transform. So it depends on in which direction you're going. So here, starting with the power spectrum, and then he has to do the inverse Fourier transform to get the autocorrelation. And this real part is just a numerical trick. Should be real. So it depends on which direction you're going. Okay, so let's look at images. So let's say that you have a perfect image. This is your ideal image. You have Gaussian noise, and then we look at the power spectrum. And the power spectrum will be a two-dimensional function, but let's look at one of the. So let's make it here. This is very good. So yeah, you know that for deterministic images, this is equal to the Fourier transform of the image squared. But this is only for deterministic. Okay? So not for noise. For noise, is the Fourier transform of the autocorrelation. Okay, so we have an image. Real space. We go to the Fourier space. Let's put it here. So we know that the spectrum will be something like that. It decays. So this is the origin of the frequency space. And now what we are doing is just taking a line of that spectrum. Okay, so that is what we are doing. So it will be a two-dimensional function, but this line will be a one-dimensional function. I will look at this. Okay, so this is for the ideal image, and this is for the noise. So for the noise, you will get something relatively flat. It is not completely flat because it is a realization. So it is just a random thing. If you repeat this process infinitely many times and you compute the average of all those lines, you will get a line. Okay, of all those profiles, you will get a line, you will get a constant. But just for one realization, what you get is something noisy. Okay, so this is the spectrum of the ideal image. This is the spectrum of the noise, and now we will overlap the two because this happens only for independent noise. So our model is that this is the ideal one plus noise. And this equation also holds in Fourier space. So in Fourier space, you have that the power spectrum observed is the power spectrum ideal plus the power spectrum of the noise. The power spectrum, the noise. That this should be the constant. And this happens only if the image and the noise are independent between each other. But if they are, they typically are, then you will add the two power spectra. And then what you see is that there are frequencies for which you have much more signal than noise, but there are other frequencies for which you have more noise than signal. So actually, that is the reason why low-pass filters are good for us, because at some point the information that I see is dominated by noise. But for the low frequencies, that is not the case. Actually, this behavior here, that it falls off as the frequency goes. It is some kind of standard property of natural images. So in natural images, this power spectrum falls as the frequency square, typically. Okay, it doesn't mean that it really has to go like this, but normally it goes with that trend. Okay, so yeah, this is the super 2, and this is the same, but now in looking at the full 2D power spectrum. So this is the power spectrum of the original image, the power spectrum of the noise, and this is the power spectrum of the addition of the two. And you already see that some of the weaker lines here, they have been buried by the noise. You don't see them anymore. And then we can highlight at which frequencies we have more noise than signal. So all these blue points, we have more noise than signal. All these red points, we have more signal than noise. And then we can overlap the two. We can see another example. So our original image, noisy image, the addition of the two. And the same with the power spectra. And at which regions we have more noise than signal, or vice versa. And then this is the justification of why to use low-pass filters. Yes.
I don't understand how you know where you have more noise than image.
Yeah.
Because you don't have the original image.
In reality, you don't have. In these examples, you have the data simulated, so you know. Yeah, but in real life, you don't know, and that is a problem. So let's simulate first, because if you simulate and you understand the simulation, you will understand what's happening in reality, and then you will try to solve the problems that you have in reality. So this is the justification of doing low-pass filters, because at some frequencies we have more signal than noise, and here we have more noise than signal. So we don't know exactly which the coefficients are. And that is why, because you don't know, but you know that on average it's somewhere here. So you adjust what is the cutoff frequency of your low-pass filter. So this is somehow the answer to your question. So you don't know exactly where this coefficient has more signal than noise. But I know that this signal contains most of my signal, or where I have more signal than noise. Okay? And you know that because you try different values and you see which one is giving better results. And so you can reject that, and then you are blurring. Yeah, because a low-pass filter is a blur. So recover, you can remove the noise, but at the cost of having a blurred image. And what if I knew exactly which frequencies I have more signal than noise? I can know this for simulated data, not for real data. But if I knew, then I could simply remove those coefficients for which I have more noise than signal, and then I would get a much sharper image. So you see that the borders are much better defined than in the standard blurring. So in the standard blurring, everything becomes more blurry, because I don't know exactly which coefficients I have more signal than noise. If I knew, I could have much better result. So again, this goes to your question. So with simulated data, you understand what I could achieve. In practice, I cannot achieve this because I don't know those coefficients. I know some region, and then that is what I can get. Okay, so we are here. So now we will complicate a bit more the image information model, and now we will include our kernel. So we have the convolution with the kernel. So let's see if we can recover the image. So so this is just to say that these kernels, they are called point spread functions, and they are related to the optical devices that we use to acquire your images. And so we will not enter into these. Probably you're seeing this with Osiris, right? So point spread functions, they are caused by the optics. Okay, so the effect of the optics is that they blur your images, and typically they blur your images. So we have some point spread function there. So how do I recover this ideal image from the observed one. This is another representation of that process. So there is an ideal image that is convolved with the kernel. This is the convolution. And then there is some noise that comes in. This is a graphical representation of this equation here. So the ideal image convolved with the kernel and then plus noise. So that is what you observe. And in Fourier space, it is the same, but the convolution becomes a multiplication. Okay, good. Then, so this is the same, but now in graphical representation in Fourier space. So you have the ideal image convolved with this one, that is the multiplication between the two, point by point. And this is what you get. So the high frequencies, you have killed them, and now you add noise and you have the addition of the two. And these are the power spectra. Okay? All the time it is the power spectra. Okay, so then, actually this is interesting. Say that I don't have noise. Okay, so if I don't have noise, the Fourier, my model is the following. So find Fourier transform of my kernel. So this equation is in frequency space. So if this is what I see. This is what I see. But can I recover the ideal? It's very easy to recover the ideal. All you have to do is ideal, the Fourier transform of the ideal is the Fourier transform of the observation divided by the Fourier transform of the kernel. You have to be careful here if the kernel has zeros in the Fourier space, because then you are dividing by zero. But otherwise, for instance, a Gaussian doesn't have zeros, so you are safe to divide by Gaussian. So you could have an estimate of how the ideal image looks like, and then all you have to do is the inverse Fourier transform here, Fourier transform -1, and then you have an estimate of what the ideal image is. This is estimate, so this is not exactly the ideal image. Okay, so can I do something similar now? Okay, so let's put a few names here. So let us call the convolution between the two, or the multiplication in Fourier space, let us call it K. So our image formation is the observation is K plus the noise. And then, given my observation, can I try to estimate K? Can I design a filter W that estimates K? And then K is I times H. So now you from once you know K, now you can recover I. So once you know K, you have estimated what K is. You can recover I by simply dividing by H. Okay, so let's decompose the problem into parts. The first part will take care of the noise. The second part will take care of the convolution kernel. Okay, so what I want is to have an estimate of my ideal image that is as close as possible to the ideal image here. And then as close as possible, again, this has appeared a few times, you can compute the least squares solution. So what is the W? What is the filter that minimizes this error? Okay, and the filter turns out to be this one. I like to write in this way. So I think it is better seen this way. It is equivalent, okay, but I think it is more clear. So the filter that I need in frequency space is H control, so H complex conjugate, and then this one plus power spectrum of the noise divided by power spectrum of my signal. Ideal. This is the ideal one. And that's it. So this is also H Fourier transform divided by H. This is Fourier transform plus 1 divided the signal to noise ratio. Okay, so let's see. So let's analyze these at two cases. So what happens when I have a very, very high signal to noise ratio? And what happens when I have a very, very low signal to noise ratio? So very, very low is when this goes to 0. And very, very high is when this goes to infinity. Okay, so when the signal to noise ratio goes to infinity, this is 1 over infinity, this is 0. And then I have complex conjugate divided by the module. So that is 1 over h. So when I have a very high signal to noise ratio, this Wiener filter behaves as just the ideal image restoration. So just dividing by the kernel, the Fourier transform of the kernel. What happens with SNR, the signal to noise ratio going to 0? So if it goes to 0, this term goes to infinity. And then I'm dividing by infinity, so this goes to 0. And that makes sense. If there is a frequency where you trust a lot your signal, just divide by the kernel. If you have a frequency for which you have much more noise than signal, then simply forget about it, put it to 0. So this is working in these regimes here, at these regimes. So if you have a frequency for which you have much more frequency signal than noise, then simply divide by h. But if you have a frequency for which you have much more noise than signal, put it to 0. And these are the two extreme cases. In reality, there is a smooth transition between the two. So it depends on what your actual signal to noise ratio is. So yeah. So it depends on what is your actual signal to noise ratio. So these are the two extremes. Actually, that equation is totally equivalent to this one. You can easily you recognize it. So you divide by I squared. I squared is the signal is the power spectrum. So if you divide numerator and denominator by I squared, then you have what I wrote. Okay, so now this is my filter. Let's undo all these steps that we have. So now, if that is my filter, you will take your observed image was J. So you will estimate K. K was the convolution of I and H. So you will estimate K by taking J, that was the observation, and filtering with W. And this is here. Okay. And now here it is all this filter times J, and then they have expressed J. And then you approximate, you say, okay, so I forget about a few terms. So if I have a very high signal to noise ratio, if I have a very high signal to noise ratio, this term will be small, this term will be small, and then the only one remaining is this one, and then I will have something that looks like I. And this is the other analysis when you have very low signal-to-noise ratio. So, but I think these analyses are more clear in that form than in the one in the slide. Okay. How did I come to that filter? How did I know that was the filter I needed? So, remind our goal. Our goal was to have an estimate I that is as close to the 2I as possible. So, this is summing overall or integrating overall frequencies, and then we simply substitute everything there. So, we put I is K divided by H. The I tilde that my estimate is Wj, so I take the observation, multiply by W, that is my filter, and then divide by H. And then you manipulate this expression. So all this is just algebra. From here to there, it is just to take this. So I will take H out, so you have it there. And then I will substitute J by K plus N. So it is just pure algebra. So down to here, it is just one to operate. So I want to find the W that minimizes this. And here it comes. So his derivation is a little bit so-so. So he starts saying, okay, so if you look at this image, so this term here includes, it has I and N. Okay, so these bars are complex conjugates. So you have, this is a kind of correlation between I and N. And if the two images are uncorrelated, then this term should be zero. And then if this term should be zero, I'm left only with this one. And here, interestingly, there is no I. So to know what the, well, there is an I implicitly here in the case. Okay, so now, how, again, the details are not shown here. How do I find the best filter? Okay, so let me write this again. We have here epsilon squared is double integral of H. I will write now explicitly the frequency. Then for it. Okay. It was okay is IH. Okay. So and then 1 minus 1. Stop. That's is that. Okay, so and then sorry. Okay, so this expression, all this integral, depends on the frequency. Yes or no? Does it depend on frequency? Yes. So epsilon squared depends on frequency. Should I write something like this here? That for each frequency is different? No, because I'm integrating in frequency, so I'm removing the dependence on frequency. So this shouldn't be done. Okay, so we shouldn't write that this is a function of frequency. So epsilon squared is a function of what? It's a function, right? So it is a function of h. It is a function of I. Actually, rather than I, it's a square here, I think. It's a square. Yeah. So rather than I, it is of this square. And it is a function also of W. And it is a function of the noise square. So it is something that depends on all these things, all these functions. And I can do the following. And again, we will omit the details, okay? But you get the idea. So I can differentiate these with respect to the filters. Bring it to 0. And then I will have my expression for W. So W is equal to whatever what I told you. This is H. We will not see the calculus details of why it is like this. All I will mention is that this is, I will write it down in this way. So all I will mention is, you know how to differentiate some functions. Normally real calculus, but there are also kind of complex differentiation. Complex differentiation. This one. Half nines. I'm looking for some kind of table of differentiation. Differentiation formulas for this is a video. Have you studied complex differentiation in the second year of calculus? No? Okay, but you know these rules of the derivative of the cosine is the sine, this kind of stuff. So there are also kind of similar stuff. I cannot find them, but there are kind of similar stuff for when you have, what is the derivative of the module squared with respect to a complex value? And there are rules for that. Okay, so to go from here to there, they are using those kind of rules. Okay, so yeah, we don't see the details of the specific calculus, but we understand the result. We understand the properties of the result. So the result is this one that I already told you. And we know how it has been achieved. And there is something very interesting here. So to know the filter or to construct my filter, I don't need to know, because if you look at our goal, what is our goal? Our goal is I want to minimize the distance between my estimate of the ideal and the ideal. I don't know the ideal, how can I do that? And the trick is that you don't need calculate that filter, you don't need the ideal. What you need is the power spectrum of the ideal. You don't need the ideal image, but its power spectrum. So all you need is an estimate of what is the signal to noise ratio at each frequency. So you don't need to know the specific function, but you need to know the signal to noise ratio. That you need to know. Okay, so let's see how we can apply that in practice. So let's say we have an image, we have a Gaussian noise, then this is the observation, and then these are the different spectra, and this is the Wiener filter. So the Wiener filter, it is somehow encoding what is the signal to noise ratio at each point. So these points here that I have a lot of signal to noise ratio will be given a lot of weight. So they will pass through our filter. And these points that I also have larger signal to noise ratio will be given again larger weights. But these ones they will be given a low weight because I don't have enough signal there. And again, this is simulated data, so I know what the signal to noise ratio is. And in reality, we have to estimate somehow, but we will see how. Okay, so this is the Wiener filter image. This is the power spectrum of the result. This is the power spectrum of the original. And now we have a couple of images, the two images. So this is the noisy one, this is the Wiener filter one. You have, so it is a little bit blurry, but those frequencies were corrupted by noise. So they were already sacrificed in their observation. And this is a nicer image than, I think we have the Gaussian black. So here we have the Gaussian black, and here we have the Wiener filter. So you see that the Wiener preserves edges much better. You see? Edges are much better preserved. Okay, very good. Now, what if we have a PSF? So now the PSF will be a Gaussian. So we have, in the previous example, we didn't have a PSF. So the PSF was just delta. Now we will have a Gaussian. So what happens if we have a Gaussian? Now, well, these are the different power spectra. And now this is my Wiener filter. So my Wiener filter, you may remember before, even these frequencies, they were contributing a lot. Now they are not contributing. Why? Because they were filtered out by the PSF. So if they have been filtered out, so the signal to noise ratio at this point is very low. So it is better just to forget about those points. They were killed by the filter. They were killed by the optical filter. So the Wiener filter cannot recover them because they were set to zero or almost set to zero. And yeah, so these are the different, and this is the result here. So this is the noisy observation, and this is the Wiener filter image. This is the original, and we can compare. Okay, so how to apply this in practice? Because in practice, we don't know, all this was simulated data, but in reality, you don't know all this stuff. So how can you do it? And here is a very interesting approach. So let's say that we have this picture here. So I want to restore it using this Wiener filter. So I have to look for the kernel, and I have to look for the noise. So for the noise, I can go to a very flat area, and the fluctuations in that flat area must be the noise. So I can take that flat area, compute the power spectrum, and now I have the power spectrum of the noise here. So how can I estimate the noise? So the noise, this original image will be something flat plus some noise. So how can I estimate the flat region? We already know how to estimate the flat region. So let's think of this in Fourier space. So that observed image, so this is frequency now. I will do it in 1D because it is easier to walk. So that observation will be made of two parts. The first part and the second. So this first part, this is just noise. And because it is very flat, very flat means very low frequency. So all I have to do is do a very low frequency filter. So I can blur these with a Gaussian. So this is the low frequency component. And now I subtract the two. If I subtract the two, what I'm left is with the noise. And because it should be flat, because I'm assuming it is an independent noise. So because it should be flat, if I estimate what this height is, noise is this way. If I estimate what this height is, I can extrapolate to this region too. Okay, so now we have an estimate of what the noise is. So I can take the high frequency components of the noise, estimate the sigmas there, and now I have different sigmas for the different channels. So now I know what the noise is. Okay, now I need the kernel. So if I need the kernel, I need something that has been convolved with my kernel. And that something could be a delta. So if I find a delta in this image, then whatever is around should be the kernel. So if you look at these bright points here, this one there, this is just a delta. And this delta has been convolved with the kernel. So I can take those values around, that should be the kernel. Now I know the kernel. I know what the power spectrum of the noise is. And then I don't have what I need also the power spectrum of the ideal image. That I don't have, but I can use the observed image as a substitute. So you have almost everything. So you have the power spectrum of the noise, you have the kernel, you have the power spectrum of the observation, and now you can construct your Wiener filter. So this was the original image, and this is the filter one. You don't see the details, but so this was the original, this is the filter one. Okay, this one is a little bit better when you look at the details. Not too much better, but a little bit better. And this is the implementation of MATLAB of the Wiener filter. So yeah, so there are ways. So your question before, in reality, you don't know these things. Yeah, that's right. But if you know by simulation, you understand what are the different components, then you will find a way to estimate what the kernel is, to estimate what the noise is, and so on. And this problem that we have seen before, here, this one here is even more complicated because you don't know the kernel. You have to estimate the kernel from the image itself. But at the end, if you read the paper, they will explain how they do it. This is our Wiener filter. By the way, Wiener is because of this guy, not Wiener. It's not. So he was a very famous mathematician that developed all this field. So this Wiener filter is called also the convolution. So these problems, we have different problems now. So we have, let's say, we have given the observed image. We always want to get the idea. Okay, so it depends on what we have. So let's say that we have the observation and the age. This problem is called the convolution. And Wiener filter is one of them. It's one of the techniques. So linear is one of them. Let's say that I don't have age. I just have the observation. And I want to get the idea. I know that there has been some convolution, but I don't know what the kernel was. This is called blind deconvolution. So maybe in some of your papers, you get this name. So blind deconvolution is because you don't have age. You have to estimate age also from your image. And that is what these people have been doing. So they have been trying to estimate what the kernel was. They have estimated that the kernel was this one. And then they have applied the convolution with that kernel and they get this. And what we have seen in the slides are the easy stuff. So the very first ways to do that. And in this paper, they use deep algorithms. So in this paper here, there. It doesn't go to the right. In the paper, they use deep learning to solve this problem. Any question?
So to find the kernel, you just have to write about units. So it's
That's a good question. So you need to know something of your image. So for instance, let me go to my publications. This one here. So you need to know something about your image. So for instance, here you see the same kind of equations we have been seeing. So the power spectrum that you should observe is a flat constant plus your filter plus the power spectrum of the noise. Then I know that only here I have some. Yeah. So again, these are 1D plots, but everything is 2D. But in the 1D you can see. So this is the power spectrum that you see. You see oscillations there. And then you know, okay, in this is an electron microscope. In this electron microscope, the focus, so not the defocus, the filter in Fourier space, is like this. All I need is to determine these parameters of that filter. I don't know what the parameters of the filter is, but I know that that filter will cause zeros or these values in the power spectrum. And then I try to find the parameters such that my power spectrum is consistent with my expectations. And then here you have probably some. Yeah. So this is the power spectrum that I see. This is the power spectrum that I predict. So you need to know something about your images. So one possibility is I know that there is a point that has been convolved with my kernel, or I know that the power spectrum should look like this, and then I find the parameters of the kernel. Or in the papers, in this blind deconvolution, they make assumptions about the compactness of my kernel. I know that my kernel is compact, and the power spectrum of the signals normally behave like this. So you have to assume something in the process. Yeah. More questions? Okay, so if there are no other questions, then we go to our exam.